So, we will be continuing with the analysis of the wire drawing operation. The detailed derivations in the last class we have discussed, and you will find that so there are a large number of expressions which has come up, because though the process of wire drawing is very simple, but the analysis of wire drawing process is very complicated, because there are many factors which are coming into picture when you are doing the analysis, mainly the friction at the workpiece die interface, the redundant deformation which takes place due to the converging die, and the die angle, due to which internal shearing of the material takes place, because there is going to be a discontinuity in the flow field. So, due to that redundant deformation also takes place, and all these factors it affects the power requirement for the drawing operation. Redundant deformation, it results in non-homogeneous deformation of the drawn wire, and this results in steep variation in the structure and properties across the cross section of the drawn wire. So, across the section itself you will find that the properties are different, and if you look at the die angle, an increase in the die angle decreases the redundant deformation. Die angle, if it is increasing then increase in the die angle increases the redundant deformation. And increase in the die angle decreases the energy for overcoming friction, because if the die angle is increased, the total contact area becomes less, so that the frictional area, frictional contact area, the interface contact area becomes less, and thereby the frictional energy becomes decreased. So, these are two opposing phenomena which is taking place, either because of the die angle. So, one is increasing the power requirement, another is decreasing the power requirement. So, in that case you need to arrive at an optimum die angle, and this has been shown in the previous lecture also, how it affects the total power requirement. So, you need to have an optimum die angle for a particular reduction depending upon the deformation. Okay. So, that the total power requirement is kept to minimum, and you will find that say in the expressions which are coming, a large number of expressions are there, has been developed by various researchers to arrive at the draw stress, the stress necessary for the drawing, and each has its own effect. But here in this case we will not be discussing all of them, but we will be discussing a few cases of them which is found suitable by a large number of people, because there is no expression which is which takes care of all matters. So, which have been widely accepted, those expressions we will discuss. We will not go into those derivations. The basics of derivation we have already discussed, but the one which is being accepted by industries and for application purpose we will discuss, and how we go ahead with it. So, in the wire drawing stresses, for the draw stress, if you wanted to find out, it is nothing but you have to calculate the stress strain for the wire drawing operation, that is epsilon w. It is based on the change in, it is based on the initial and final length, because you are just extending the rod or a wire. So, due to that there is a reduction in the cross sectional area, there is an increase in the length, which initially in the fundamentals of metal working we have discussed. So, this during wire drawing operation, epsilon w is we can write it as log say your LF by L naught. So, in terms of cross sectional area, that we can write it as log A naught by AF. This naught stands for the initial, original, and F for the final, the suffix. Okay. So, which we will be following throughout this lecture. And instead of strain, the term which is extensively used is the fractional reduction in area. The fractional reduction in cross sectional area R is defined as S naught by A f by A naught. Okay. So, this is equation number 1, this is equation number 2. From this we can directly correlate between your strain and the fractional reduction as the epsilon W is equal to log 1 by 1 minus R. So, in terms of fractional reduction in area we can write it. And the drawing stress sigma d can be obtained from the work done by the force F, the total pulling force F by the final cross sectional area. Okay. So, that we can write it as in this form, a beta into say your average flow stress over the strain which is taking place into log 1 by 1 minus R. Okay. Where beta where the sigma bar is the average flow stress over the strain interval. And beta is a factor whose value lies between 1 and 3. If beta is equal to 1, so for beta is equal to 1, you will see that sigma d is equal to say sigma bar log 1 by 1 minus R, which is nothing but 1 by 1 minus R, which is nothing but the stress necessary for homogeneous deformation or the stress necessary for homogenization. But since this redundant work and what is that frictional energy is coming into picture. So, that is why this beta, for a simplicity in the simple form we have introduced this beta. So, so that will give an idea about what is the beta is the ratio of the total work to the homogeneous. So, that means beta is nothing but the ratio of total work done for drawing to the energy for homogeneous deformation for the same reduction. And this factor beta we can also express in the form of an efficiency factor such that now beta is equal to an efficiency factor. This instead of that beta can be expressed in terms of an efficiency factor eta, which is nothing but 1 by beta. So, it is just represented in a different way. And this beta, the efficiency factor eta consists of two factors, consists of one an efficiency due to the redundant work loss and second eta f, the efficiency due to frictional losses. So, that means beta is equal to this phi plus f. So, if you just look at this from this as a basic, this is the most simplest form of representation of the drawings, provided we know the efficiency factor, or if you know that beta value. Any of these things, if you know, you can find out what will, because in the expression the stress necessary for homogeneous deformation is there. Other things are based on this, you are multiplying with the efficiency factor. Okay. So, now let us look at the drawing stress involving friction and redundant work. Okay. What are the things? You will find that several expressions have come up, because earlier our derivation was simple with the friction, redundant work we did not come, and we also discussed about in a wire drawing operation how we can find out the redundant work from a simple stress strain curve of a fully annealed wire, and also a material which has been drawn to this particular reduction, and from that if you shift it and superimpose it, how much it comes. So, epsilon star that we have found due to the drawing operation, from that we can find out the redundant deformation. But it is always it may not be true, because it will not take care of the variation in the strain across the cross section. So, that is one major problem which is coming, and it also takes, most of this case takes only for a single drawing operation. Multiple drawing operation, it becomes very complicated, it is not behaving in a proper way. So, you will find several expressions have been proposed to account for the friction and redundant work and the geometry of the die. These three factors are interrelated, and that drawing stress necessary depends upon all these three factors. One of the expression which has been widely accepted is by Seibel. So, where the draw stress sigma d which is nothing but the total force by the final cross sectional area, they have expressed in terms of your mean flow stress or average flow stress in this way. It is equal to 1 plus mu by alpha into log A naught by AF. So, this is 1 by 1 minus r, okay, plus 2 alpha by 3. So, this relationship people have arrived at. So, this we can write it as expression number 4. In this, you will see that mu is the coefficient of friction, alpha is the semi die angle. If it is a converging die like this, the material is being drawn like this and it is coming out. So, this is the 2 alpha, or we can say this angle is alpha, okay. This is 2 alpha. So, the semi die angle is alpha, and in this last term it takes care of the redundant deformation. 2 alpha by 3, it takes care of the redundant deformation, okay. But you have to be very careful in using this expression. You see that it is coming, all other things are there. So, if there is a small difference in the inaccuracy in your average flow stress, this is going to what is called magnify in a big way in the total draw stress. So, one has to be very careful that, okay. So, this equation, equation number 5, it deals with the redundant work by adding an extra term to the basic equation. Basic equation is for your homogeneous deformation, that is this part, okay. So, these extra terms are being added, and there is some merit in dealing with the redundant work by using a multiplying factor on the basic equation for draw stress in the presence of friction, okay. So, two mostly used equations are, another two equations are sigma d is equal to sigma bar into which we have discussed in the previous class, I hope, into phi 1 into log A naught by A f. You will find that these more or less all these things are of the similar way. And another expression is that sigma d is equal to sigma bar into 1 plus b by b into phi 1 log phi 1 into, these are all expressing in different way, that is 1 minus A f by A naught to the power b. So, this is expression 7, where b is equal to mu cot alpha. Mu is the coefficient of friction and alpha is the diangle, okay, semi-diangle. So, the in equation 6, the term 1 plus b into phi 1 has the same meaning as your beta here, has the same in equation number 4. So, it is almost the same. Okay. And so we can say that is similar to or same meaning to beta in equation 4, or we can say that 1 plus beta, 1 plus b, we can say is equal to 1 by this F, frictional force, because b is nothing but it's a function of your coefficient of friction. Okay. Whereas this phi 1 is nothing but 1 by your this efficiency due to redundant work loss. And you will find that when the product when b into epsilon becomes very small, what was that equation number? Equation 7 approaches equation 6, almost to equation 6, not completely. And we should know this what is this phi 1. So, phi 1 is related to the geometry of drawing, that means your deformation zone geometry. So, that is a linear function of the what you call it as that parameter delta, that means phi 1 is equal to k 1 plus k 2 into delta, where this parameter delta which we have discussed, I think it may be in the lecture number 3 or 2 or 3, I do not remember exactly, that deformation, I think it is lecture 3. So, in this so that can be related for your wire drawing operation as the d naught plus df, the final diameter, by d naught minus final diameter into sin alpha, which you can say it is almost equivalent to 4 alpha by w, by epsilon w. And this is it's a linear equation with respect to this parameter delta, the deformation zone parameter delta, and that is satisfied. It's a linear relationship up to, so it is satisfactory up to say delta is equal to 6. Up to a value of delta is equal to 6. equation 8 is satisfied. But beyond that, if the delta value goes beyond that, if you recollect that one curve, one graph I have shown it, which was taken from Dieter book, that with up to very high value also there. But beyond that, what happens that the linearity is lost, so we will end up with a lot of errors in the prediction. And you will find that lot of work has been done, some values of K1 and K2. So maybe we can write it as in a table form. We can write say K1 and K2 in the annealed condition. If you look for materials, say for example copper, brass, this is 1 and 0.27, and brass is also same value 0.27, and mild steel it is 0.8 and 0.09, and aluminum you will find that it is 0.8 and 0.09 from experimentally determined values of K1 and K2. And if you take say 20 after 25% strain hardening, so copper and brass it is 0.88 and this is 0.19, whereas for aluminum it is 0.88 and this is 0.22, K2 is 0.22. So that way we can find it from the literature different values, and then we can find, you see that there is not much variation, but it is satisfactory by using these equations. And by using this equation 6 and 7, any of these equation on the using this mean yield stress, whether this is a correct value where the predictions are going to be right. So people did investigators carried out extensive work, and then they found that if you are using this mean flow stress in these equations, if you are using the mean flow stress as sigma bar over the strain following the Holloman relationship, that means sigma is equal to A epsilon raised to n or K epsilon raised to n, whatever you, in whichever form you write. And if you are satisfied with that and taking the average stress value, you found that using the average stress value, the draw stress which was obtained was an underestimation. However, the error which comes through by using of the underestimated by using the mean flow stress is only 10%. So when it is 10%, it is almost acceptable, okay, by investigators. So you don't have to spend too much of energy and time on having a very accurate prediction of the draw stress required, because your machine also has a limitation. So that is what their conclusion said. Now we also discussed that the minimum die angle for minimum work. See, there are two opposing trends. If the die angle is small, your the work, and for a particular, for a constant reduction, if the die angle is small, then your workpiece die workpiece interface area is large. So that will result in very high frictional force. So frictional force will increase with the reduction in the die angle. But if the, as I have drawn earlier also, if you look at the metal flow condition, it will just come, take a turn like this and go. So your internal shearing becomes. So with the low die angle, the velocity discontinuity will be reduced. So that means internal shearing will be reduced. That will result in the less amount of redundant work for when you are using low die angle. But with the die angle increasing, see, for example, if you take a 90-degree die, 2 alpha is equal to 90 degree and you are trying to pull the material like this, the metal which will be flowing will be like a dead metal zone will come and then there is an internal shearing which is taking place. Okay. So, here you will find a dead metal zone. So, large amount of energy will be spent for this redundant work with the diangle. But the thing is that the frictional force will be reduced considerably. So, these two opposing trends come. So, when you look at it, you have to have a minimum diangle, and several empirical relationships and derived relationships were also proposed. One by Westrich was that the minimum diangle alpha star is equal to, in this lecture I am not going into derivation of all these things, so that these details can be used for practicing engineers. So, mu into your reduction by 1 minus r, where r is the reduction in cross sectional area. This is a very simple expression and it is so simple, but it can be used to have a first hand estimate of the drawing stress. That is the biggest advantage of using this relationship. And you may see that from this expression, this alpha star, that the minimum diangle is dependent only on your mu and reduction. Okay? And so, that is the diangle will depend only on the coefficient of friction and reduction. It will not be depending upon the precise work hardening behavior of the material. What is the work hardening exponent? It is not interested. It is not interested in what is your strength coefficient of that, or the constants in the Hollow Mount relationship. It is not dependent. That means, it is not dependent upon the deformation behavior of the material itself or flow stress of the material. It completely depends upon the coefficient of friction at the die workpiece interface and the reduction which is required. So, that is one advantage of that. Now, having come across this, after deformation, if you know the deformation behavior of the material, then you can also have an idea about what is going to be the draw stress. But you will find that after drawing operation, there is going to be a longitudinal stress across the cross section. If it is circular, across the diameter, if it is rectangular, across the thickness, there is going to be a variation in the longitudinal stress, because stresses are there, longitudinal stresses are developed because of the tensile stress, the plastic deformation is taking place, and due to which, and it is plastic deformation taking place, so longitudinal stresses will be there. You will find at the center stress is higher than at the surface. Okay, the longitudinal stresses. At the wire surface, the stress is lower, whereas at the center, the stress is high. Okay, and sometimes at the center, the stress which are developed is higher than your applied stress also, applied drawing stress. So, that means, if you look at the mean stress, based on that, if you compute, you will find that at the center it may be still higher than that. So, the excess stress on the center line above that required for drawing, okay. So, we can say that is given by the difference between the center line stress sigma max and the average draw stress. So, minus F by AF is, researchers have arrived at this value by 3 into 1 plus mu by alpha into 1 by log A naught by AF. Okay. So, this is that excess stress on the center line above that required for drawing, that is given by the difference between this the maximum center line stress which is going to have and the average draw stress required that. See, this differential stress across the cross section, see that center it is large, the deformation is very large and tensile strain is taking place, whereas at the outer surface the stress is very less. So, it will try to compact, but the center is trying to deform more. What will happen is that at the center of the sample during drawing, you may end up with a chevron cracking. So, a cracking at the center will take place in the presence of tensile stress. If it is above certain limit, it will result in center line cracking. It has the shape of a chevron shape. Okay? So, you know that what is chevron shape. Chevron, that shape is there. So, that cracks may develop, and the parameters by which these cracks can develop is, one is small reduction, second is large diangle, third is the work hardened metal, so it depends upon all these three. So, this is equation number 11. So, this is the general expressions, and the minimum axial tensile stresses. This comes as axial tensile stresses during drawing operation. That is fine, we have arrived at this, but how to determine the redundant work? This is very important. Okay? So, we wanted to know how this redundant work can be estimated. So, one method we have explained earlier was that you take a material in a fully annealed condition and find out what is its stress strain curve, flow curve, and then when it is coming, maybe after some amount, you will find that you find out the stress strain curve for the drawn wire, and you will find that in the drawn wire for the same reduction, the yield strength is high because of the internal shearing and other things. So, you shift it towards the right, displace it so that it matches with the stress strain curve, and then when it matches with that, how much is the increase in the strain, epsilon star, okay, corresponding to equivalent strain epsilon. From that you find out what is the excess strain which has taken place. So, that is what and the ratio by this you will get the value of phi 1. Okay, that is what we discussed. But this is not a very accurate method also, but in a very simple technique we can find out. But there are other methods of finding out the redundant work is there. So, they are for finding out the value. So, estimation of redundant work and redundant deformation. The method, the first method 1, we have several methods, I will just discuss one or two methods. The method 1 is based on the determination of the redundant deformation phi 2, based on determination of redundant deformation phi 2 for redundant work phi 1. Okay. So, this phi 2 we have to find out and then correlate with the phi 1. So, phi 1 is equal to 1 minus exponential minus phi 2 b epsilon w divided by 1 minus exponential minus b epsilon w into phi 2 to the power n. This way we can find. And you will find that this product B into epsilon W is almost equal to say 4 mu by delta. So, if this is very small, sufficiently small, then phi 1 is equal to phi 2 to the power n, where n is the work hardening exponent. Exponent of the relation, which is nothing but sigma is equal to say maybe k epsilon raised to n. Okay, so that is that work hardening exponent which is coming. So, you should understand the difference between phi 1 and phi 2. So, phi 2 has been termed redundant deformation. It is not the redundant work, it is a redundant deformation to distinguish it from phi 1. So, phi 2, I will write it, phi 2 is termed as redundant deformation. And this is a measurement of the extra strain as a result of redundant deformation. That is what. So, equivalent strain, we are reaching that. If you refer back to that lecture, maybe third lecture or second lecture, I am not sure, in the basic fundamentals of plastic deformation, if you look at it, effect of diangle and other things we have come across, there you will find that redundant deformation is defined, and I have very clearly mentioned that how to determine that epsilon star. Okay. So, and this is the measure of extra deformation or maybe equivalent strain. Sustained by the rod. Or wire compared to the nominal strain. What is nominal strain? Nominal strain is for the uniform homogeneous deformation. That is homogeneous in the wire drawing pass. Here we can say epsilon W. So, that means you can define this epsilon star as nothing but phi 2 into epsilon W from the stress strain curve for a what you call it as annealed material. See, if you just take this case, it is like this. This is for the annealed material, and then for you may find that after a strain of epsilon and take this, you will find that it is just raised 1. So, if you just if you move this up to here, it will match with this. Okay. So, this is called as the epsilon strain. So, if you translate this into this region, so you are getting this epsilon strain. So, that is this relationship which you are getting here, okay, from this relationship. So, that is what you should understand, that this is the redundant deformation and not redundant work. So, this phi 2 can be related with your deformation zone geometry, okay, as C1 plus C2 into delta. This is also a linear equation similar to the phi 1 also you are getting, where phi is defined by equation earlier we have mentioned. So, df minus d naught d naught minus df by that relationship, where is that equation number 9. So, this relationship. And it is very interesting to note that when you do a large number of, when it was a large number of experiments were conducted, and with a wide work hardening characteristic, on materials having wide work hardening characteristics, this C2 and C1, they can be correlated by to its work hardening exponent, as C1 is equal to 2.25 into your n raised to 0.28 into k is equal to minus 0.10, and C2 is equal to, I will just not write it down, 0.367 n raised to 0.76 k raised to minus 0.054. So, this is 17. So, with a wide variation in work hardening behavior with n and k, where sigma is equal to k epsilon raised to n. This is the flow stress relationship. You will find that for large number of materials, when you do it, the C1 and C2 is coming like this. So, that is a very interesting thing, so that we can find out the C1 and C2, and then from that, if you know the deformation zone geometry, that parameter delta, from that we can calculate the phi 2, and then from that we can determine phi 1. This is one method of determining the deformation, redundant work. Another is method 2. In this, what happened is that the stress strain curves are drawn at different conditions. You are obtaining the stress strain curve for drawn wire, maybe like you have drawn for different reduction, and then they are compared with the stress strain curve of a fully annealed steel. Okay. Then the initial flow stress following any given strain in wire drawing is greater than the flow stress produced by straining homogeneously to the same strain in simple tension. So, that is what you will find out, and this difference is due to the redundant deformation. So, if the stress strain curves drawn at different conditions are compared to the stress strain curve of annealed material, then what will happen? The drawn wire will always have a higher stress for a particular strain. Then the drawn wire will have higher stress for a constant strain. Compared to your homogeneously deformed tensile pulled sample, what is the in that condition. Okay. So, this difference is due to the redundant deformation, and the the strain in simple tension corresponds to the yield stress of the drawn wire, is thus an equivalent strain epsilon star, which we have discussed. So, you will find that for a number of metals, this epsilon star can be correlated by the nominal strain by EW plus K2 into your sin alpha. So, if you use the relationship 14, okay, this 14 if you use it, then you can get that say phi 2 is equal to k 1 plus k 2 into sin alpha by epsilon w, you can get it. This is suffix w. Okay. So, if you just plot that epsilon star versus epsilon plot, we will have k 1 as a slope, we will have say slope as k 1 and intercept on epsilon star axis as k 2 sin alpha. This advantage of this method is that only 2 data points are required for one particular value of alpha, because it is a straight line equation. So, one particular alpha, you just take say for 2 reduction and then get the value, and then you can get the value of k 1 and 2. So, it becomes very simple. Hence, phi 2 can be determined for any diangle. So, that way it is very, very convenient. So, and if you look at that from equation 15 and 19 are identical and using equation 9 so we can get C1 is equal to K1 and 4C2 is equal to K2. A very good approximation we can get it, okay, for all practical wire drawing operations. Now, next is the method 3. That also is a very convenient form of determining the work function. In this, you measure the hardness of the drawn wire across the cross section. Okay. Measure the hardness of wire across the transverse section. In a continuous form, you measure it at equal spacing and then get a plot of that. Okay. But before that, the material, you just homogeneously you deform, do a tensile test maybe for some reduction of 5%, 10%, 20%, 30%, 40%, like that for different reductions, you just get a series of experiments done. So, deform it to say different reductions. So, that because it is a tensile pulling, then you can easily get the equivalent strain there and section it after each reduction, find out the hardness of that material because it is deforming in a homogeneous form. So, find out the hardness of that material. So, you will get a plot of hardness versus strain. For homogeneous strain, for the hardness versus homogeneous strain, you can get a plot. And now, in your sample, after drawn wire, you section it, and across the section, like if it is a circular piece, along the diameter, you just find out what is the hardness here at these different points, and if this is a center, so you can say this is say 1, 2, 3, 4, like that you can say 1, 2, 3, 4. So, along the across the diameter, if it is rectangular piece, across the thickness you measure that. So, then at this point, you just take the value of the this hardness and correlate it to its equivalent strain from maybe your say for this homogeneous strain with the hardness, maybe like something it will come. So, from this value you can just find out what is the hardness at 1, 2, 3, 4. Okay. So, in that case you can always find the equivalent strain for the cross section, the equivalent for the whole cross section, that is epsilon star. Can be determined by graphical integration. So, from this master plot you measure this and then you find out what is this epsilon star 1, epsilon star, I will draw it in a bigger way. So, you can say epsilon star 1, epsilon star 2, epsilon star 3, epsilon star 3, 4, like that you can get it the value across the our drawn wire, and then this value, the equivalent strain for the whole cross section area, you can find out by graphical integration. Okay. And the ratio of epsilon dot star to the nominal wire drawing strain will give the value of phi 2. See, once you get this relationship, no, this hardness versus this one. So, we can say that the strain versus, so that can be you fit a curve for this, it can be plotted as A h raised to n, m we can put, n we are using this, so here we can say h, and this is. So, this similar to what is that similar to that. So, this h instead of the strain you can convert it into h, so that becomes very easy. Only you have a master curve, you develop it first conducting some experiment, and after that, for any value you can find out what is this equivalent strain. The ratio of epsilon dot bar star we can get it, and from that from this ratio to your nominal strain will give you the value of phi 2. Once phi 2 is known, you just look at it whether B into E is large or small, and then from that we can find out. Okay. This technique is very satisfactory for a single pass wire drawing operation. For single pass wire drawing operation this is satisfactory, but for a multi pass this is not found that much suitable, okay, or satisfactory. The reason which is still not being established. So, with this for today we will talk. Next we will have some practical classes, so some problem using this part which we have discussed.